All right, gentlemen, today we're going to talk about solving systems algebraically, and we're going to talk specifically about an elimination method. Now, the first method we talked about was graphing, and we want to understand why graphing is not always the best. If you have to get an equation in slope-intercept form, that takes some time, and if it doesn't intersect at an obvious coordinate, it might not be the best method. Substitution is only going to be the best method when we have a coefficient of 1. So for all other problems, I think elimination is going to be our easiest method. All right, this screen here gives all the steps for the elimination method. This is a good screen to pause. I'm not going to take a ton of time on this. First is you always have to get the equations in ax plus by equals c form. Both equations have to be in that form. That way everything lines up neatly for us. Then we need to make opposite coefficients with either the x or the y variables. To do this, you can multiply the entire equation, so both sides, by a number. Sometimes you're going to have to multiply both equations by different numbers to do that. Once you have opposite coefficients, you're going to add the two equations together. You cannot add the equations together until you have opposites. I do not recommend subtracting. Once you have opposite coefficients and you add the equations together, one variable will always cancel, which leaves you with one variable left, and you can solve for that variable. Just like we did in substitution, once we have that first value, we can plug that back into the original and find the second value, which we're going to write as an ordered pair. Then we always want to check to make sure the solution works in both equations. For our first problem here, we see right away that we have both equations in ax plus by equals c form. Then we check to see if we have opposite coefficients, and we do. We have opposites with positive 3y and negative 3y, so what I'm able to do is add the two equations together right away. 2x plus 4x gives us 6x. 3y plus negative 3y cancels. Bring down the equal sign. 1 plus 29 gives us 30. We now only have one variable to solve for, so we can continue to solve for x, and we get x equals 5. Now we're going to take 5 and plug it into either of the originals. I'm going to use the first one since it's smaller numbers. We have 2. We're going to plug in 5 for x. And we're going to write the rest of the equation out just like we did in substitution. And now we're going to solve this for y. So we get 3y equals negative 9. Divide both sides by 3. And we get y equals negative 3. So our final answer we want to write as an ordered pair. It'd be 5, negative 3. And again, before we circle that as the final answer, we do want to check it and plug it into both of the original problems. And this one will work out. 5, negative 3 is our intersection of these two lines. Our second problem here, again, both are in ax plus by equals c form. And again, we are started with opposite coefficients, so we can add these two equations together. 11x plus 12x gives us 23x. The y's added together will cancel, and that 20 plus 3 gives us 23. We only have one variable we can solve, so we get x equals 1. Then we're going to plug that in. I think maybe the second one's easier, so 12, plug in 1, minus y equals 3. 12 minus y equals 3. Subtract 12 from both sides. Negative y equals negative 9. Divide by negative 1. And we get y equals 9. So our final answer again is an ordered pair, 1, 9. Check to make sure it works in both, and it does. So again, this linear system of equations intersects at exactly one point at 1, 9. Our third example here is the first one. I make you guys work a little bit. So first, the first equation is in ax plus by equals c form, but the second equation is not, so I need to move that 2x to the other side. So I get negative 2x plus 4y equals 4. And what I'm going to do now is bring down this first equation so that it's right with it. 3x minus 4y equals 2. And what I'm going to do is add these two equations together since I have opposites. My y values are opposites. So I get x, my y's cancel, equals 6. There's nothing to solve for. I got that value. So now I'm going to plug that into, let's say, the first one. So we have 3 times 6 minus 4y equals 2. 3 times 6 gives us 18. We are then going to subtract 18 from both sides. Negative 4y equals negative 16. Divide both sides by negative 4. And I get y equals positive 4. So again, my final answer is an ordered pair, 6, 4. Check it in both of the equations, and it works in both. That's our final answer. All right, so our final problem in this video is, before we start it, I want to take a second to remind you that, yes, we could do graphing, we could do substitution, but I would never suggest that for this problem specifically. First of all, to get both of these in slope-intercept form, they'd both be 2 steps. You'd have to deal with some fractions in there. To do substitution, you would also deal with fractions. You don't have any coefficients of 1, so right away you should rule out substitution. Now, elimination isn't the easiest here because even though they're both in ax plus by equals c form, you don't have any opposite coefficients. So your job is to create them. So what I mean by that is you can look at the x values or the y's and get both of them to be opposite. So we want to think about the least common multiple of 4 and negative 5, or of negative 2 and positive 3. Now, I'm going to use the y values just because they're smaller numbers. So I'm going to think, okay, what number does 2 and 3 both go into? Well, they both go into 6. So how do I get from 2 to 6? I got to multiply by 3. Now, if I multiply the first equation by 3, my y value will be negative 6y. So I need the second one to be a positive 6y. So I'm going to multiply by 2. Now, this is really important that when you multiply these numbers in, it goes to every single thing in the equation. That's the only way we make it an equivalent equation. So I'm going to write that first one below. So the 3 gets distributed to everything. So we have 12x minus 6y equals 6. And the second one, we distribute the 2, we get negative 10x plus 6y equals 2. Now I'm able to add these two equations together so that I get 2x, my y values cancel, equals 8. And now it's everything that we've seen in the last 3 problems where there's only one variable, so we can solve for x. And right away we know x equals 4. And now we finish it the same way as in the past, where we take that 4 and plug it into the originals. You could also actually take this 4 and plug it into x in these new equations. But most of the time, those new equations are going to be larger numbers. So I would, again, just recommend going back to the original. So I'm going to use the first one just because it's positive. So 4, plug in x or 4 for x. And now solve this for y. Subtract 16 from both sides. I'm going to swing this up to the other side. So I get negative 2y equals negative 14. Divide both sides by negative 2. And I get y equals positive 7. Again, my final answer has to be an ordered pair. So x is 4, y is 7. I would double check to make sure they work in both of the originals, and they do. And that's our answer. So that's the toughest problem you could see using the elimination method. Again, could you get fractions and decimals using this method? Absolutely. But again, I think it's easier. I think it's the easiest of the three methods. All right, and the last thing here is, in order to get credit for this, I will need to see tomorrow in class. I will need to see the 4 problems and the steps written down. If you show that to me at the beginning of class, I'll give you guys the points for watching this video. Thanks a lot. Bye.